general, the National Electrical Code, or NEC, uses ampacity as the basis for sizing conductors. However, there are a few exceptions to this rule. One of these exceptions is the sizing of grounding electrode conductors as specified in Table 250.66 of the NEC. The reason for this exception is that the size of the grounding electrode conductor is not determined by its ampacity, but rather by the size of the largest ungrounded service entrance conductor or the equivalent area for parallel conductors. It's crucial to understand that the grounding electrode conductor is not intended to carry current under normal operating conditions. Instead, its primary purpose is to provide a low resistance path to ground for fault currents. Fault currents are abnormal currents that occur during electrical faults, such as short circuits or ground faults. These currents can be very high and can cause damage to equipment and injury to people if they are not properly managed. Using the area of the service entrance conductors, or equivalent area for parallel conductors, as the basis for sizing grounding electrode conductors ensures that the conductor will be capable of safely handling the maximum fault current that is likely to occur. This is a critical safety measure. A properly sized grounding electrode conductor plays a vital role in protecting people and property from electrical shock and fire by providing a path for fault currents to flow back to the source, allowing overcurrent protection devices such as circuit breakers or fuses to quickly trip and de-energize the circuit. The code mandates this approach for several reasons. Firstly, fault current magnitude isn't easily predictable and can far exceed normal operating current. Secondly, the grounding electrode conductor might need to carry this high fault current for a short duration. Basing the size on the upstream service conductors ensures it can handle that surge. Thirdly, the area calculation provides a simple, conservative, and readily verifiable method for ensuring adequate grounding capacity. To understand this better, let's delve into some key concepts. Ampacity refers to the current carrying capacity of a conductor, which is the maximum current a conductor can carry continuously without exceeding its temperature rating. This rating is influenced by factors such as the conductor material, size, insulation type, and ambient temperature. Tables like 310.16 in the NEC provide ampacity values for various conductor types and sizes under specific conditions. Conductor area, typically measured in circular mils or square millimeters, relates directly to the amount of conductive material available to carry current. When conductors are installed in parallel, their ampacities are combined to determine the overall ampacity of the circuit. However, for grounding electrode conductors, the equivalent area of the parallel conductors is used in Table 250.66 to determine the required size of the grounding electrode conductor. Grounding electrode conductors connect the electrical system to the earth, providing a path for fault currents to return to the source. These conductors are typically connected to grounding electrodes such as ground rods, metal water pipes, or building steel. Table 250.66 provides minimum sizes for grounding electrode conductors based on the size of the service entrance conductors. It's important to note that the table specifies different minimum sizes depending on the type of grounding electrode used. The NEC provides rules about grounding to ensure electrical systems are safely grounded. Grounding means creating a low impedance path to the earth. This protects people from electric shock and helps electrical equipment work safely. Grounding electrode conductors connect the electrical system to grounding electrodes. These electrodes are things that make good contact with the earth, like metal water pipes, steel building frames, or ground rods. The size of the grounding electrode conductor is chosen using specific rules in the NEC. We use Table 250.66 in the NEC to find the minimum size of the grounding electrode conductor. This table uses the size of the service entrance conductors to determine the size of the grounding electrode conductor. The service entrance conductors bring power from the utility to the building. The grounding electrode conductor must be large enough to safely carry fault currents back to the source. Fault currents are high currents that flow when there is a short circuit or ground fault. These currents can be dangerous and cause damage to equipment if not properly handled. The grounding electrode conductor provides a low resistance path for these currents to flow back to the source, which allows overcurrent protection devices like circuit breakers to quickly trip and disconnect the circuit. The size of the grounding electrode conductor is also important for ensuring that the grounding system can effectively dissipate static electricity and other unwanted electrical noise. A properly sized grounding electrode conductor helps to maintain a stable and reliable electrical system. In situations where parallel conductors are used for the service entrance, the NEC requires that the equivalent area of the parallel conductors be used to determine the size of the grounding electrode conductor. The equivalent area is calculated by adding the areas of the individual parallel conductors. For example, if two 300 kcmil aluminum conductors are used in parallel, the equivalent area would be 600 kcmil. This equivalent area is then used to determine the minimum size of the grounding electrode conductor from table 250.66. There's a common question of why we don't use ampacity for grounding electrode conductors like we do for many other conductor sizing applications in the NEC. The key reason is the nature of fault currents. Fault currents are short-duration, high-magnitude events. The grounding electrode conductor's main job is to handle these transient surges, not continuous current flow. A conductor size solely based on ampacity might not have the physical mass to effectively dissipate the heat generated by a large fault current, even if the duration is short. The cross-sectional area, which is what table 250.66 utilizes, provides a more direct correlation to the conductor's ability to handle the thermal stress imposed by a fault. Another reason for using area instead of ampacity relates to the different operating conditions. Ampacity tables, like 310.16, are based on conductors operating under specific ambient temperatures and insulation conditions. Grounding electrode conductors, on the other hand, may be exposed to a wider range of environmental conditions and may be buried directly in the earth. It would be impractical to develop ampacity tables that account for all of the possible installation scenarios for grounding electrode conductors. By using the size of the service entrance conductors as a proxy for the potential fault current, table 250.66 provides a simple and conservative approach to sizing grounding electrode conductors. Furthermore, the use of area simplifies the calculation process, especially when dealing with parallel conductors. It avoids the need to consider the ampacity dilating factors that may apply to parallel conductors in other applications. In summary, while ampacity is a fundamental consideration for sizing conductors that carry continuous current, the sizing of grounding electrode conductors is primarily based on their ability to safely handle fault currents. Table 250.66 uses the size of the service entrance conductors, or the equivalent area of parallel conductors, as a practical and conservative method for ensuring that grounding electrode conductors are adequately sized to handle the thermal stresses imposed by fault currents. This approach helps to protect people and property from electrical hazards. The NEC is updated regularly to reflect changes in technology and best practices. It is important to consult the latest edition of the NEC for the most up-to-date information on grounding and bonding requirements. Grounding and bonding are crucial for electrical safety. Proper grounding and bonding help to prevent electrical shock, fire, and equipment damage. Therefore, understanding and following the NEC requirements for grounding and bonding is essential for all electrical professionals. Now, let's explore the specific application of table 250.66 with parallel conductors. When service entrance conductors are run in parallel, it means multiple conductors are used per phase or neutral to increase the overall current carrying capacity of the service. This is often done when the required ampacity exceeds the maximum ampacity of a single conductor. When sizing the grounding electrode conductor for parallel service entrance conductors, the NEC requires you to use the equivalent area of the parallel conductors. This means you need to add up the cross-sectional areas of all the parallel conductors for each phase. For example, let's say you have two 500 kcmil copper conductors per phase. Each 500 kcmil conductor has an approximate area of 500,000 circular mils. Since there are two conductors in parallel, the equivalent area would be 1 million circular mils or 1000 kcmil. You would then use this equivalent area of 1000 kcmil to determine the minimum size of the grounding electrode conductor from table 250.66. The reason for using the equivalent area is to ensure that the grounding electrode conductor is sized appropriately for the total potential fault current that the parallel service entrance conductors could carry. Even though each individual conductor in the parallel set may have a lower ampacity and the total ampacity of the service, the grounding electrode conductor needs to be sized to handle the worst-case scenario where a fault occurs on all of the parallel conductors simultaneously. This approach provides an additional safety margin and helps to ensure that the grounding system can effectively clear fault currents. It's important to note that when calculating the equivalent area of parallel conductors, you should use the actual cross-sectional area of the conductors, not their ampacity. The NEC provides tables with the approximate area of different conductor sizes. You can also calculate the area based on the conductor's diameter. For accurate calculations, it is recommended to consult the conductor manufacturer specifications. In practice, the process of sizing a grounding electrode conductor involves several steps. Firstly, determine the size and material of the service entrance conductors. Secondly, if the service entrance conductors are run in parallel, calculate the equivalent area of the parallel conductors. Thirdly, refer to table 250.66 in the NEC to determine the minimum size of the grounding electrode conductor based on the size or equivalent area of the service entrance conductors. Fourthly, select the appropriate type of grounding electrode, such as a ground rod, metal water pipe, or building steel. Fifthly, ensure that the grounding electrode conductor is properly connected to the grounding electrode in the service equipment. Finally, verify that the grounding system meets all applicable NEC requirements. It is also crucial to consider the type of grounding electrode being used, as table 250.66 specifies different minimum sizes for different types of grounding electrodes. For example, the minimum size of a grounding electrode conductor connected to a ground rod may be different than the minimum size of a grounding electrode conductor connected to a metal water pipe. Furthermore, the NEC provides specific requirements for the installation of grounding electrodes, such as the depth and spacing of ground rods. These requirements are designed to ensure that the grounding electrode provides a reliable connection to the earth. Remember, grounding electrode conductors are not intended to carry current continuously. Their main purpose is to provide a low impedance path for fault currents to return to the source. It is imperative to size the grounding electrode conductor based on the size of the service entrance conductors or the equivalent area of parallel conductors as specified in table 250.66. This will help to ensure that the grounding system can safely handle fault currents and protect people and property from electrical hazards. Also, local codes might have stricter requirements than the NEC, so always check them too. Consider a building with a 480 volts, 3-phase service. The service entrance conductors consist of 3 sets of parallel 500 kcmil copper conductors per phase. To determine the minimum size of the grounding electrode conductor, you would firstly calculate the equivalent area of the parallel conductors. Since there are 3 500 kcmil conductors per phase, the equivalent area would be 1500 kcmil. Secondly, you would refer to table 250.66 to determine the minimum size of the grounding electrode conductor based on an equivalent area of 1500 kcmil. According to table 250.66, for service with copper service entrance conductors with an equivalent area of over 1100 kcmil, the minimum size of the grounding electrode conductor is 3/0 copper. Thirdly, you would select the appropriate type of grounding electrode, such as a ground rod, metal water pipe, or building steel. The NEC provides specific requirements for the installation of grounding electrodes, such as the number and spacing of ground rods. Fourthly, you would ensure that the 3/0 copper grounding electrode conductor is properly connected to the grounding electrode and the service equipment. The connection must be made using approved methods and materials. Fifthly, you would verify that the grounding system meets all applicable NEC requirements. This includes verifying the resistance to ground of the grounding electrode system. The NEC requires that the resistance to ground not exceed 25 ohms. If the resistance to ground exceeds 25 ohms, additional grounding electrodes must be installed. In addition to the minimum size requirements in Table 250.66, the NEC also provides other requirements for grounding electrode conductors. For example, the NEC requires that grounding electrode conductors be protected from physical damage. This can be achieved by running the grounding electrode conductor in conduit or by locating it in a protected area. The NEC also requires that grounding electrode conductors be continuous and without splices. If a splice is necessary, it must be made using an approved method. It's also important to understand the relationship between grounding and bonding. Grounding and bonding are both essential for electrical safety. Grounding provides a path for fault currents to return to the source, while bonding ensures that all metal parts of the electrical system are at the same electrical potential. Bonding helps to prevent electrical shock by eliminating voltage differences between metal parts. The NEC provides specific requirements for bonding, including the size of bonding conductors and the methods for making bonding connections. The NEC also provides requirements for equipment grounding conductors. Equipment grounding conductors are used to ground non-current carrying metal parts of equipment, such as motor frames and appliance housings. Equipment grounding conductors provide a path for fault currents to return to the source in the event of a ground fault. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. Proper grounding and bonding are essential for electrical safety. By following the NEC requirements for grounding and bonding, you can help to protect people and property from electrical hazards. Remember to always consult the latest edition of the NEC and local codes for the most up-to-date information on grounding and bonding requirements. Also consider the specific requirements of the equipment being installed, as some equipment may have additional grounding requirements. Remember to consult with a qualified electrical professional for assistance with any electrical work. Electrical work can be dangerous, and it is important to ensure that it is performed safely and correctly. A qualified electrical professional can help you to design and install a grounding system that meets all applicable requirements. In conclusion, the NEC uses ampacity as the basis for sizing most conductors, but the sizing of grounding electrode conductors is an exception. Table 250.66 uses the size of the service entrance conductors, or the equivalent area of parallel conductors, as a proxy for the potential fault current. This approach ensures that the grounding electrode conductor is adequately sized to handle fault currents and protect people and property from electrical hazards.